And the last talk of this session is learning discriminative video representations using adversarial perturbation, and the presentation will be given by Anoop Cherian.
Okay, good afternoon, everyone. I'm Anoop Cherian. I'm a researcher at MERL, and this is joint work with my intern and student, Wang from the Australian National University. So in this talk, we are looking back at the classical problem of video action recognition, where we are given a set of training videos, and each associated with a single action label. We need to learn a representation for each video, which is then used to train a classifier. We assume the whole framework is end-to-end trainable. So with the advent of deep learning methods, there have been significant advancements on this problem in the recent past, such as the emergence of the two-stream networks, the inflated 3D models, the temporal segment networks, the spatiotemporal multipliers, and so on. So this is a typical pipeline of action recognition CNN model. So as it may be practically difficult to keep all the frames in a video in memory during the training or in the inference time, typically the methods take spatiotemporal patches from the video and then use these patches to train a deep learning model. And the deep learning models produces some sort of features. And then these features are aggregated in a pooling layer, and then that generates a representation. That representation is used for action classification. So typically, all these things are done in an end-to-end fashion, and these different modules are kind of layers in a typical neural network. Now, one thing that is important is all these different methods that I reviewed earlier, and whatever has been happening is more or less focused on different deep learning architectures for better feature extraction. And the focus of this talk is on better representation learning. That is, we assume that that there is some neural network that generates useful features. And then how do you aggregate these features to generate a better representation, which can be useful for training action classifier at a later point. So that's the goal of this talk. So what could be a good representation? A few desirable properties for a good representation could be that it's compact. That is, it should be able to fit it in memory to train another layer of a network or something, or it should be efficient to be computed. It should kind of capture the arrow of time. That is because it's action, so there is a kind of a temporal dynamics happening in a video. So you should be able to capture that in some way. And it should summarize inputs well so that you don't miss out on any important characteristics of the video when you train a classifier later on. And some of the typical approaches for this are the pooling. Standard pooling approaches are like the average pooling, the rank pooling, or you can train a recurrent neural network on top of these features, or temporal convolutions, and so on. So the key insight in this talk is basically that maybe not all features produced by a CNN are useful for recognition, and there can be so much of redundancy in the whole set of features. And if you can actually come up with some sort of filtering or pruning mechanism that can remove a lot of unnecessary dimensions of features, that can perhaps help the subsequent classifier layer to learn better action recognition models. So that's a key insight. And so to get to that, here are some. So we formalize this problem in the coming slides. So suppose that you are given an input matrix, which is x, and x has columns as the features from this CNN model. And suppose that you have access to some sort of a noise set, which I'll get into, which is a critical component, and which I'll get into later on. So let's assume for now that there is a Z matrix, which is a kind of a noise set. And the idea is to use the Z set to actually extract useful features from X in some way. Now, we use, in this talk, support vector machines, basically. So suppose you have a binary classification problem, and you have this X, which is the input features that you get from your CNN run on the input video. And then you have the Z matrix, and you want to classify X from Z in a binary classification setup. And so that is what this hyperplane learned by the CNN by the SVM is doing. And this W can be looked upon as some sort of so if you know what a support vector machine is, I mean, it actually learns this hyperplane W, which is actually a linear combination of all the input points. And those points which are not support vectors have a weight of 0. So it's sort of like doing average pooling, weighted average pooling, where weights are 0 for some of the items which are not support vectors, and a value for those which are used as support vectors. So it's kind of ultimately doing some sort of a filtering of points which are not useful for this problem, and collating only those ones which are being used, are useful. So we could perhaps use this W as a representation for your input data. So that is the crux of the algorithm. This mechanism was actually published earlier this year in CVPR, and we call it the discriminative pooling. Now, using a single hyperplane might not be sufficient because it has limited capacity, but maybe your data features are kind of very nonlinear, and your single hyperplane is insufficient to capture everything about the video. So maybe you can switch to a kernelized SVM, but then kernelized SVM is kind of difficult to be parameterized in the kind of framework that we are looking forward to. So then we thought, OK, what about multiple hyperplanes? So you can have a discriminative classifier where you have different hyperplanes oriented in different directions, so perhaps orthogonal directions, and they span different parts of the data, and again, in a binary classification setup. And then maybe you can use this matrix, which is a subspace matrix, with, say, k columns, and each column is orthogonal to each other. And maybe that matrix can be used as a representation for your input data. So that is a discriminative subspace pooling that we are proposing here. Now, the critical question is, how do you select Z? Because Z is a set that you want to use to extract the good features from your input data. So, so here we use this mechanism called the universal adversarial perturbations, which was proposed by Musavi Dasfouli in CVPR 2017, and they actually show that if this kind of an optimization problem, where you want to find the minimum perturbation that can be added to your input data, and that will misclassify a very well-trained classifier. And since you are basically looking for the minimum perturbation, minimum strength perturbation, basically this optimization problem is looking at those features or patterns or dimensions of your data which are highly sensitive to such misclassifications or sensitive to generating errors. And so we thought, maybe what if we try to use this? So we created our Z set, which is a noise set, as the original data input features added with the perturbations generated on a well-trained CNN classifier for action recognition. And now the question is, why do we think this is interesting? So to find the minimal perturbations, like I said, the optimization needs to look for those data features that are very sensitive to misclassification. And thus, the universal perturbations as of a negative back forces the discriminative subspace pooling to use these sensitive features for representation learning. Now, technically, our scheme learns a subspace of such sensitive dimensions, which are perhaps similar for all videos, because this universal perturbation is generated from an action classifier CNN model, which is on some data. So maybe the videos which have that particular actions also share some sort of similarities in the subspaces which are sensitive to perturbations. So in such a sense, maybe the subspaces are useful representations in general for this kind of task. So now coming to the overall architecture of our system. So basically, you have input videos, and you extract features from it. And then you have CNN trained on the actions in general, and then you create adversarial perturbations. You create these two sets, the X and Z, and then learn a discriminative subspace separating the two classes. And then use these subspaces as representations for your videos. So this whole thing can be formulated in this optimization problem, where basically you are looking for the subspace, which are orthogonal matrices. And you want to actually minimize, or you want to learn the subspace hyperplane. So here the max, the highlighted max actually says that one of these hyperplanes must be able to classify a given data point to this positive or negative class, binary class. The second max, the outer max, actually captures the max margin of the hyperplane. And then we also have some temporal consistency criteria that when data points are projected onto these subspaces, they should have temporal ordering constraints to capture the temporal dynamics of the actions. So once we solve this optimization problem, you get a W matrix, which is used as a subspace representation. And this, since it's an orthogonal matrix, it's not a Euclidean object. It lives on something called a Stiefel manifold. And so you define your action classifier on the Stiefel manifold. Now, how do we, so again, it's a non-convex optimization problem. So to solve it, we resort to some Riemannian geometric approaches. So we specifically use something called Riemannian conjugate gradient. The idea is that suppose you start with some subspace, W0, on the Stiefel manifold, and then you create a tangent space of that, and then compute a Euclidean gradient in the usual sense of taking the gradient of your objective. And this gradient can be in some direction away from the manifold. So you want to actually map it back to a Riemannian sense and then project it back onto to the manifold using some sort of exponential map. You do this iteratively and then convert in orthogonal directions because it's Riemannian conjugate gradient and land up somewhere which satisfies some optimization criteria for stopping. So that's pretty much our overall algorithm. And coming to the experiments, so we tested this on different types of video recognition tasks. For example, we tried this HMDB51, which is the state-of-the-art action recognition dataset. It has about 6,000 videos, and we used a two-stream model for encoding the features. So two-stream in the sense that we take RGB single frames and stacks of optical flow, which is kind of a standard practice in this area. And we tried two different architectures for this. One is ResNet 152 and the recent I3D features, which are kind of the state-of-the-art. Then on the other data set is NTU-RGBD, which are skeleton sequences. So there are about 57,000 sequences, 60 action classes. We use a temporal convolutional network to encode these sequences. In the third data set, it's actually the YEP++, which is a video texture classification data set. It is split into video textures taken from a static camera and one taken from a dynamic moving camera. And for that, we actually use the Inception ResNet V2 architecture. So all these different data sets use different architectures just to show that our system scheme is kind of agnostic to any kind of CNN architecture you might have. So now, first of all, we wanted to validate how good this adversarial perturbations are. So we ran some experiments using that optimization that I showed, with using adversarial perturbations and with, say, using Gaussian random noise. And we see that there is a consistent improvement in performance by about 2 to 3%. And as you increase the number of hyperplanes in your subspace, the performance increases, but then it saturates. Also, the temporal consistency criteria that we impose is also kind of very important for this, for improving the performance. The next experiment is on what if you change the fooling rate of this perturbations. For increasing the fooling rate means that the optimization for computing these perturbations are getting more and more confident of what it is being fooled to. So increasing the fooling rate actually increases the performance. This is of video recognition, which means that maybe increasing the fooling rate is actually pushing this optimization problem for adversarial perturbations to find those dimensions which are very, very sensitive to perturbations, and then use using those subspaces are perhaps going to be very useful for the representation learning problem. So again, comparison to the state of the art. So we did some results. We show some results on comparison to most of the recent methods on action recognition. We outperform most of them by 2 to 3%. We also outperform our own previous methods, which were published earlier this year, generalized rank pooling and discriminative pooling, and some of the recent methods on two-stream I3D and spatiotemporal multipliers, etc. Our performance on I3D with this on the whole HMDB data set was maybe less than about 0.6%. So we actually wanted to investigate why this is not as much as what we would expect in comparison to other state of the arts. So we analyzed this, and we found that if the sequences are longer, then if you combine I3D with our discriminative pooling scheme, performs much better than I3D with average pooling. So I3D plus average pooling is what is typically used. So longer the sequences, this performs better, which is kind of intuitive because you need to learn some parameters, subspace parameters in our scheme, and you need to have sufficient input features to learn that. So you need to have longer sequences for having that. Now here are some visualizations of our scheme. So we actually visualize how the subspaces look like. So the first column is actually the input. This is the input video, and we visualize the first hyperplane, which is a single image, and the fifth hyperplane that it generates. And surprisingly, we found that the first and the second hyperplanes are sort of capturing the appearance information in the videos, and the 3, 4, 5, and 6 are capturing mostly the dynamics information. And so that has been consistent in several of the videos that we tried, and which kind of is surprising, but then it actually means that it is actually splitting the interesting information in the videos into different subspaces and tackling the representation in a segregated way. So in summary, so we proposed to represent videos using discriminative subspaces. Each column of these subspaces act as a classifier separating the input features from the noise set. Now, to generate the noise set, we compute universal adversarial perturbations using a trained CNN model. The perturbations find subspaces that are vulnerable to misclassifications. Our experiments using the proposed representation show state-of-the-art performance. Now, if you have any questions or clarifications, please visit us at poster number 88. Thank you.
We have time for one short question. Okay.
Hi. So I was wondering if you had a chance to compare your approach to network compression techniques that exist out there to identify what are the salient features, basically use them for your classification task.
I'm not very familiar with the network compression side of things, so we haven't done that so far. But that's probably an interesting thing to try in the future. Thank you.
Okay, let's thank all the speakers of this session.